In today's video, we're going to look at dividing polynomials. As you can see, we have a couple goals here. We're going to learn about long division on the one method of dividing polynomials. The second method will be synthetic division. And then we're going to learn two theorems that use dividing of polynomials, the remainder theorem and the factor theorem. And then we're going to put this all together, and then we're going to go the other direction. And if we have the zeros of polynomial, we're going to find the equation of that polynomial. So to kind of introduce this, I'm going to go back to some terminology that we learned in our last video. So we're given this polynomial f of x here. As you can see in the graph, you'll notice that this polynomial has some zeros. And you definitely I've noted 1 0 here. The other 0 is not as pretty, but we have a 0 at 2. So because we know there's a 0 at 2, we know that it has the factor x minus 2 as part of its equation. So that means that there exists a second degree polynomial such that the original function f of x is going to equal to that factor x minus 2 times this other factor, we'll call it q of x, which is the quadratic equation. And so how do we find this mystery q of x function? Well, how you find that q of x function is simply by long division, or dividing the polynomials. So let's do that. Let's divide the polynomial f of x by x minus 2, its factor, to see what we get. So long division is simply you take your polynomial and make sure, the key is here, you got to make sure the x's decrease by 1 degree each time. So I have an x cubed, an x squared, an x to the first, and then no x. So it's decreased by 1 each time. And then you divide your factor x minus 2 into this. And then to do this, all we're doing is we're looking at a first term and a first term. And we're asking ourselves, okay, what can I multiply x by so it equals 6x cubed? Well, that's pretty easy. I can just multiply that by 6x squared. And then you do that. So I take 6x squared times x gives me 6x cubed. And then 6x squared times a negative 2 gives me a negative 12x squared. And then you subtract this polynomial from the one above. So 6x cubed minus 6x cubed is 0. By design, that first term should always be 0. And then a negative 19x squared minus a negative becomes positive 12x squared. So negative 9x squared plus 12x squared gives us a negative 7x squared. And then just like you did in long division in elementary school, now you bring down the next term and repeat. So what can I multiply x by so that is equal to negative 7x squared, looking at the first terms here? And well, I can multiply that by negative 7x. So negative 7x times x is negative 7x squared. Negative 7x minus 2x is positive 14x. And then subtract those, and that gives us 0. 16x minus 14x gives us 2x. We'll bring down the next term. What can I multiply x by so that's equal to 2x squared? 2x. Well, I can multiply that by a positive 2. So 2 times x is 2x. 2 times negative 2 is negative 4, and then subtract that, and I get 0. So that's our q of x that we were trying to find. Our q of x is at 6x squared minus 7x plus 2. So I figured out that our original function, 6x cubed minus 19x squared plus 16x minus 4 is equal to x minus 2 times 6x squared minus 7x plus 2. All right, so that's what I figured out so far. But then it says, use your result to factor the polynomial completely. All right, so notice I've gotten this down to a quadratic. Well, we all know how to factor quadratics. So I have that first factor I did long division with. And then 6x squared minus 7x plus 2 will factor to 3x minus 2 times 2x minus 1. And so the original trinomial, I now have factored completely to this term. All right, so let's get some terminology down a little bit. So f of x and d of x are polynomials, such that d of x cannot be 0, and that's because I'll be dividing by d of x. As you can see down here at the bottom, f of x divided by d of x, so we cannot divide by 0. We learned that in our unit 1. And the degree of d of x is less than or equal to the degree of f of x. And then there exists a unique polynomial q of x and r of x such that f of x divided by g of x, okay? So we call f of x, that term that we're dividing into, is our dividend. And the term that we're dividing by, d of x, is called our divisor. The answer we get, the q of x term, the answer when we do our division is called our quotient. if we get a leftover, last time we had a remainder of 0, but if we have something that's left over, it's called our remainder. And how do we write our answer? So we write our quotient plus our remainder divided by our dividend. So we will have that fraction left over and we make a fraction. Okay. Now when r of x equals 0, or the degree of r of x is less than the degree of d of x, okay, if the remainder r of x is 0, then d of x divides equally or evenly into f of x. And then we say d of x is a factor of our original function if it divides equally like we did the last one. And it's a 0 of the polynomial. Okay, so before you can apply the division algorithm, follow these steps. Okay, as I said in my first example, write the dividend and divisor in descending orders of x. Descending powers of the variable. Okay, so that's extremely important in order to do this. If you don't have one of the orders, like if you don't have, you go straight from x cubed to x, and so you don't have an x squared term, you have to insert placeholders. Okay, and you just write that missing x squared term with a 0 coefficient, 0x squared. Okay, and that works it out. So in this case, notice we're going to use long division, divide x cubed minus 1 by x minus 1. So my dividend is x cubed, but it don't have an x squared term, so I have to do plus 0x squared. I have an x term, so plus 0x minus 1. And our divisor is x minus 1, degree of 1. So let's check this. So my dividend has degree 3, 2, 1, 0. So that one checks out. And then my divisor has degree 0, 1. I mean 1, 0. So yes, that one checks out. So that's how we set it up. And again, start by asking yourself, what can I multiply x by to get x cubed? Well, that's just x squared. So it gives me x cubed minus x squared. And we subtract this, and we get x squared plus 0x. And then start again. What can I multiply x by to get x squared? Well, that's a positive x. Make sure you put the signs in between up here. That gives me x squared minus x. Subtract that. That leaves me with an x minus 1. What can I multiply x by to get x? 1. That gives me x minus 1. Subtract that, and I get 0. So I have a remainder of 0. So it tells me that x minus 1 is the divisor of this. But since I use long division to divide this, this is what here on the top is my answer to the problem. All right, let's see how you did on your example problem. All right, so you were asked to divide x cubed minus 2x squared plus 0x, had a place over there, minus 9, into x minus 3. X will go into x cubed, x squared times. So it gives me x cubed minus 3x squared, and then I have to subtract. Gives me an x squared, bring down the next term. I can multiply x by to get x squared, a positive x. So it gives me an x squared minus 3x. Subtract that. And that gives us a positive 3x minus 9. What can I multiply x by to get positive 3x? Positive 3. So I get a 3x minus 9. Subtract that, and I get 0. So that you should have got the answer of x squared plus x plus 3. All right, now that we know how to do long division, let's see if we can do what's called synthetic division. This synthetic division is just a shortcut to long division. Now, it only works well if you have a binomial, what you're dividing by, and if, in fact, if you have a binomial that has a coefficient of 1. So if we have something, if what our divisor is something like x minus k, then this works well. Now, if I have x plus k, for our formula, remember that's going to be x minus a negative k. So we're going to be using a negative k when we do this outside. All right, so say I have this polynomial ax cubed plus bx squared plus cx plus d. Okay, and I'm going to divide it by x minus k. Now, how you set this up is you take these coefficients of your dividend, and that goes here. So I'm taking the x's away and just writing the coefficients. All right, so this is the coefficients of the dividend. And then on the outside, we have x minus k. So on the outside, I'm just going to write k. Now, the process for this is you're going to drop down that first coefficient. It always comes straight down. And then after you drop down the coefficient, you multiply the outsides together. So k times a gives me ka. So I write that down. And then I'm just going to do whatever operation in this column is. So in this case, I'm going to take b plus ka. And whatever that answer is comes down to, whatever that b plus ka, that comes down here. And then I'm going to repeat k times b plus ka goes up in this. So multiply across, you multiply diagonal, and then you add or subtract straight down. Okay. What you get here, these terms I get here are going to be my coefficients of my quotient, my answer. And then we're gonna put our x's back in. So we took the x's out, and then at the end we're gonna put our x's back in. And we always put our x's back in by 1 power less than what we started with. So when I put my x back in with this a coefficient here, it's gonna be ax squared. So it's always gonna be a power different. Now, the last little coefficient that you get down here, that right here is gonna be our remainder. And then you'll write that over your divisor to write your remainder as you do the pattern. So basically the pattern is, the vertical pattern you add, go up and down, like this. Our vertical pattern, we add terms in the columns. And our diagonal pattern is we multiply the result by our k. Alright, so that's kind of abstract and it might be hard to follow, so let's do one. We're going to divide this polynomial x to the fourth minus 10x squared minus 2x plus 4 by x plus 3. Okay, so first thing I gotta do is put in any place errors. So I don't have a x cubed term. So again, make sure that 4, 3, 2, 1, 0. Coefficient has to be counting down like that. So when I set up my divisor here, I'm going to take the coefficient of x to the fourth, which is 1, coefficient of x cubed, which is 0, coefficient of x squared, which is negative 10, coefficient of the x, which is negative 2, and then the constant term. Okay, that's what goes inside. Now I have x plus 3, so that's understood to be x minus a negative 3. So negative 3 goes on the outside here. I drop down that first term, multiply negative 3 times 1 to get negative 3. 0 minus 3 is negative 3. Negative 3 times negative 3 is positive 9. Negative 10 plus 9 is a negative 1. Negative 3 times a negative 1 is positive 3. Negative 2 plus 3 gives us 1. Negative 3 times 1 is negative 3. 4 minus 3 is 1. Put that last one in a box. Okay, and so I started with x to the fourth, so I'm going to take this bottom line here, 1, and put the x back with it, so it's going to have 1x cubed minus 3x squared, and I'm just decreasing power of x each time, minus 1x plus 1. So that's my quotient, and then in the box here is my remainder. So plus 1 over my divisor of x plus 3. And that would be my answer using synthetic division. Now, notice that this one, the coefficient is not x. So you got to do a little work before you figure out what's going to go on the outside of your divide sign. And all you do to figure out what goes on the outside is you set this equal to 0. Because notice this shortcut here I did with this pattern to get negative 3. I could have said x plus 3 equals 0. Subtract 3 from each side and said, okay, negative 3 goes on the outside. So we're going to do the same thing here. So I'm going to subtract the 5 and then divide by 2. So actually negative 5 halves goes on my outside over here. So, and then I'll check my powers of my x cubed, squared, 1, 0. So I don't need any placeholders. So 10, negative 11, negative 72, and 45. And we're going to divide by negative 5 halves. Okay, so we bring down our first term, which is 10, and negative 5 halves times 10 gives us a negative 25. And then we'll subtract these and to get a negative 36. Negative 5 halves times a negative 36 is a positive 90. Negative 72 plus 90 gives us 18. 18 times negative 5 halves is negative 45, which is 0. So this one has remainder 0. So I know it is a factor of the original polynomial. It divides equally into it. So what would I write as my answer? That's going to be 10, and I start with 1 power less, so x squared, minus 36x plus 18. And I don't have any fraction left over because there's no remainder. Now it's your turn to try one. All right, so let's see how you did. So looking at my degrees of polynomial x cubed, squared, 1, and 0, so I don't need any placeholders. I'm just going to take those coefficients, 8, 6, negative 89, and 60, and then x plus 4 equals 0, so x equals negative 4 goes on the outside. Bring down the first, negative 4 times 8 is negative 32, negative 32 plus 6 is negative 26, negative 4 times negative 26 is 104, minus 89 is 15, negative 4 times 15 is negative 60, which gives us a remainder of 0. So my answer, putting the x's back in, is 8x squared minus 26x plus 15. Make sure you put the x's back in. That's your answer. Now that we know how to divide polynomials using either synthetic division or long division, next I want to learn is something called the remainder theorem. Okay, so if a polynomial f of x is divided by x minus k, then the remainder r is equal to f times k. Well, that's a powerful statement. So the remainder when you do synthetic division is the function value at whatever that value that you're looking at. So I can use this to find my function value. So we can use synthetic division and the remainder theorem to evaluate f of x at f of negative 1. So what we learned in the last unit is we just replace every x with negative 1 and simplify down. So that's one technique. Now our new technique is I can take this f of x, now again, notice that my degrees are 3, 2, 1, 0, so I don't need any placeholders. And I can put that in my synthetic division, 4, 10, negative 3, and negative 8. And I want to find f of negative 1, so I put negative 1 out here. And do my synthetic division. Drop the 4 down, negative 1 times 4 is negative 4. Adding that to 10 is 6. Negative 1 times 6 is negative 6. Add that together equals negative 9. Negative 1 times negative 9 is 9. Negative 8 plus 9 is 1. So this is my remainder. So the remainder also gives me my function value. So therefore, f of negative 1 is 1. And then you can also do this by checking that into, you can do what we learned last unit and just replace every x with negative 1, simplify it down and see what you get, and you'll find out that you get the same. But often the synthetic division is a lot easier to work with. So I want you to try this next one using synthetic division and the remainder theorem. So as you can see, this would be pretty easy to do. All I have to do is take 4, 10, negative 3, and negative 8, because my powers are decreased. Outside goes the 4, because I want to figure out f of 4. So drop down, 4 times 4 is 16, that's 26. 4 times 26 is 104, minus 3 is 101, times by 4 is 404, minus the 8 is 396. So therefore, f of 4 is equal to 396. Now that was a much faster and a little bit easier to do than figure out what 4 cubed is and 4 squared. 4 cubed times 4 plus 10 times 4 squared, and that can get some pretty large numbers. So this is a shortcut that can be a little bit easier. All right, now we're going to learn something called the factor theorem. I've kind of already been talking about that as we've gone through it, but this just kind of formalizes it. So how do you know if you have factors? Well, a polynomial f of x has the factor f minus k if and only if our f of k gives a remainder of 0. So basically, if you do the synthetic division and what comes in the box is 0, it's a factor. So I know here, since I got 396 as an answer, that x minus 4 is not a factor of this polynomial from our last example. So that's how you figure out if it's factor or not. If you get 0 as a remainder, it is. So we're going to show that x minus 2 is a factor of this polynomial. So I'm going to do synthetic division, and again, I'm checking that's x to the 4, 3, 2, 1, 0, so I don't need placeholders. I just take those coefficients. And then we have x minus 2, and so positive 2 goes on the outside. Drop down that first term, 2 times 2 is 4. 7 plus 4 gives us 11. 11 times 2 is 22. 22 minus 4 is 18. 18 times 2 is 36. 36 minus 27 is 9. 9 times 2 is 18. Negative 18 minus that is 0. So checked. So I know that x minus 2 is a factor. Now, to check if x minus 4 is a factor, I can go back to the original polynomial if I want to, or I can take this smaller one and do synthetic division with it. So we can start making our degrees a little bit smaller. It's going to become very important later on. So I'm just going to take negative 3 and divide it into this answer I got in my last problem. So the 2 comes down. 2 times a negative 3 gives us a negative 6. We have 11 minus 6, which is 5. 5 times negative 3 is 15, negative 15. 18 minus 15 gives us 3. 3 times a negative 3 is negative 9. 9 minus 9 is 0. So check. So now I know that x plus 3 is a factor. By our factor theorem showed that. So that's how you do it. Now, and notice this is the reason why this is so important that I continue using the smaller ones. I started with a degree 4 polynomial. And then when I divide it by the factor of x minus 2, here is a degree 3 polynomial. So now I'm down to a degree 2 polynomial. So this here is a degree 2 polynomial. So when I put my x's back in, this is going to be 2x squared plus 5x plus 3. So I have a quadratic. And quadratics we can easily simplify by factoring or using our quadratic formula. And so this one would factor to 2x plus 3 times x plus 1. And so basically I figured out that our original function f of x is equal to our factor x minus 2, our factor x plus 3, and when I factor the quadratic, 2x plus 3 and x plus 1. So this is a complete factorization of our original polynomial. And now we can factor bigger polynomials than just quadratics. So I'm going to pause and let you do this one. All right, so degrees of f of x is 3, 2, 1, 0, so I don't need any placeholders. So I got 1, -6, -13, and 42. And if my factor is x minus 2, then that means 2 goes on the outside. Bring the 1 down. 1 times 2 is 2. That gives us a -4 times 2 is -8, which gives us -21 times 2, which is -42, remainder of 0. So yes, it is a factor. So I've shown that x minus 2 is a factor. It's got a remainder of 0. Now, this is the polynomial x squared minus 4x minus 21. And so that's a quadratic. It will factor. It actually factors to x minus 7 and x plus 3. So I can say the complete factorization of f of x is x minus 2 times x minus 7 times x plus 3. So let's kind of put all this together in this problem here. So given that this f of x function, and we know that we want to verify that x plus 4, the square root of 3, is a factor and x plus 3 is a factor. We want to find the remainder theorem for f of x, and then we want to use our results to write the complete factorization of f of x. All right, I'm going to start with x plus 3 because that's a little bit easier to do for part A. And so I have 3, 2, 1, 0. So it goes equally, so I don't need any placeholders. And so I have 1, 3, -48, -144. X plus 3, so that means -3 comes out when I set that equal to 0 and solve. So 1 times -3 is -3. 3 times 3, so we got 3 minus 3, which is 0. This is 0. That's -48. -48 times by 3, -3 gives us a positive 144. So I have a remainder of 0. All right. So I started with x cubed. So I've verified that. Now here I'm going to show you another way to verify, especially this cubic one, the square root one that's a little hard to do synthetic division with. Well, let's put our x's back in. So I know this is the same as x squared. There's no x term, so minus 48. And then we're just going to solve this quadratic. So x squared is equal to 48. X is equal to plus or minus the square root of 48. 48 does simplify down. I know 4 will go into 48 12 times. So 4 is a perfect square. 12 I can break down as 4 times 3. So I got 4 that comes out with remainder square root of 3. So I know -4 plus the square root of 3. So this translates to x is equal to 4 the square root of 3, or x is equal to -4 the square root of 3. Now that's my zeros. So to find my factors, remember I just move this over the other side, get it equal to 0. So I have a factor of x minus 4 the square root of 3, and I have a factor of x plus 4 the square root of 3. And that's what I wanted to verify, that that is 1. So yes, we verified that it is 1. So there's another technique that you can use to verify. So find the remainder of factors. Well, I just did that. So our remaining factor or factors in this case is x minus 4 the square root of 3. We found it already. Use your result to write the complete factorization of f of x. So f of x is equal to our first factor, which was x plus 3, times the 2 factors we found from the quadratic equation, x minus 4 the square root of 3, and x plus 4 the square root of 3. There's the complete factorization. D, okay, list the zeros. Well, the zeros, we take each of these factors and set them equal to 0 and solve. So if I take, let me give myself more room. If I take x plus 3 equal to x is 0, get x equals -3. X minus 4 the square root of 3, set that equal to 0, get x equals 4 the square root of 3. And x plus 4 the square root of 3, set that equal to 0, I get x is equal to -4 the square root of 3. So my zeros is negative 4, the square root of 3, negative 3, and 4, the square root of 3. If I write it in increasing order, or when you can also write negative 3 plus or minus 4, the square root of 3. Either way that you want to write it. There's my zeros. Confirm your result by using your graphing calculator and graph the polynomial. So basically, all I want you to do on that is to go to your graphing calculator here. And in y equals, you just plug in your equation. So let me clear this. Okay, so our original equation was x to the third minus 6x squared minus 13x plus 42. Zoom 6. All right, so here we're looking at a polynomial. You can zoom out if you want to see kind of what the polynomial looks like. That's kind of the polynomial look like. But I kind of like this zoom pretty close to it because all I'm looking at is where it's crossing the x-intercepts. And so I can do my trace and I can just plug in my zeros I found. So am I doing the right equation? No, I'm doing the wrong equation. So we have x cubed plus 3x squared minus 48x minus 144. And our zeros are negative 3 plus or minus 4, the square root of 3. I did the wrong equation. Let's try this again. I was doing the last equation. All right, so x cubed plus 3x squared minus 48x, x cubed plus 3x squared minus 48x minus 144. I knew the graph didn't look like it should have looked. All right. So then all I want to do is I want to do trace. And I'm going to trace. All right, trace. And we'll do a negative 3. And look, we get y value of 0. So that verifies it. And then trace. And we're going to do 4 the square root of 3. Enter. And notice I get negative 1.136 e to the negative 13. So that just means I have that move that decimal to the left 13 times. So I got point with 0, 0, 0, 0, 0, 11, 12 zeros, and then 1. And so it's not exactly 0, but it's very, very close. And that's because the pixels on your calculator is so small, so large that we can't get the exact value. So we assume that's approximate 0. So that's close enough to 0. So that verifies. And then back to trace. And we're going to do negative 4 the square root of 3. And enter. And then that's also 0, approximately 0. So yes, we verified that those are zeros. Okay, pause while you do this one. Okay, we're going to start with A, and we're going to verify that each of these are factors. So I notice my powers of my x's are decreasing by 1, so I don't need any placeholders. So that's 1, negative 4, negative 15, 58, and negative 40. And I'm going to start with x minus 5, so that means I have a 5 out here in the divisor. And so bring the 1 down. 1 times 5 is 5. That gives me a 1, 5, negative 10. That gives me a negative 50. That gives me 8. 8 times 5 is 40. And so a remainder of 0. Verified. And then I'm going to continue on with this same dividing sign here to keep breaking it down to smaller powers of x. And now I'm going to use negative 4 on the outside. So I'm going to bring the 1 down. That gives me a negative 4, which is negative 3, which is positive 12, which is positive 2, and negative 8, remainder of 0. So that's A, we've verified. B asks us to find the remainder theorem, the remainder factors of f of x. So I started up here with x to the 4th. So this means it's x cubed, so this means it's x squared. So putting the x's back in, it becomes x squared minus 3x plus 2. And so I'm just going to factor this, and it factors to x minus 2 and x minus 1. So that's the remainder theorems, the remainder factors of this. And then write f of x as the complete factorization. So the factors I verified was x minus 5 and x plus 4, and the factors I found was x minus 2 and x minus 1. So there's the complete factorization of this polynomial. Okay, D, list our zeros. X is equal to negative 5. Oops. Not negative 5, positive 5. So x is equal to negative 4. Okay, and then positive 1, positive 2, and positive 5. So there are zeros. And an E is on your calculator, verifying those by doing your graph the calculator, trace, and plug in each of these and make sure you get a Y value of 0. So I'm not going to show that, but that's your verify, and it does verify. Now we're going to go the other direction. So we're going to find a polynomial of degree 3 that has the following zeros. 0, positive square root of 2, square root of 3, and negative square root of 3. So how you find the original polynomial is you take each 0 and just say x equals it. So x equals 0, x equals square root of 3, and x equals negative the square root of 3. Now get all these set equal to 0. So this one's already set equal to 0. So we have the x. So that's good. This one I'm going to subtract the square root of 3 to get my 0. And here I'm going to add my square root of 3 to get it equal to 0. Once you have those equal to 0, each of these are factors now. So my factors of this function would be x times x minus the square root of 3 times x plus the square root of 3. So that's the complete factorization of this polynomial. So that's how how we got the C, the complete factorization. Now to get our original polynomial, we're just going to multiply. Now anytime you have square roots together, you want to start with those. So I'm going to keep that x out to the side and just do the full method. X times x gives me x squared plus x the square root of 3 minus x the square root of 3. And then negative square root of 3 times positive square root of 3 gives us negative square root of 9, which is 3. So I have x times x squared minus 3. I ran out of room. Is what we got our factorization, because these terms cancel out, and then multiply each term by x to get x cubed minus 3x. So our original polynomial was x cubed minus 3x. So I'll pause while you do this last example. All right, so start by saying, okay, we got x is equal to negative 12, or x is equal to negative 6. So set this equal to 0 by adding 12 to each side, and then set this one equal to 0 by adding 6 to each side. So my first factor is x plus 12, my second factor is x plus 6. So I'm going to multiply these together, get x squared plus 6x plus 12x plus 72 gives me x squared plus 18x plus 72. So the quadratic, the equation of degree 2 that has these two zeros would be x squared plus 18x plus 72.